Continuing where we were yesterday. So like in algebra, geometry is also going to use numbers, variables, and operations. So there's some things that we need to know here. For segments, we're going to use congruent segments or equal segments. Both of those two things are important ideas to understand. Angle measurements. So these mean the angles are congruent, and these means their measures are equal. These are really specific differences between what these are. This means that we have two segments that are exactly the same. This statement really only refers to the length of the segment. These two segments have the same length. Now, more or less, they kind of mean the same thing, but it's important to know the distinction. Same here. This is saying we have two angles that are exactly the same shape and size, and this is saying that the angle measurements are the same. Slightly different, but also kind of mean the same thing. So just knowing kind of what is being said and how we might use those things differently. All right, so here is a problem here. We're starting off with a segment with some labeled dimensions, and what we're trying to do is solve for x. So we're going to figure out what the value of x is. This right here is our given information, so we don't know anything other than this picture, which is a lot. From this picture, we can tell we have 3 points. They're all collinear, they're all in a straight line. We have this segment is x plus 3, from L to M is 2x minus 1, and the whole thing is 5x minus 4. This is a problem from chapter 1 that we used what's called the segment addition postulate. So we would write an equation like this, where we say Km, the whole segment, is equal to these two pieces added together, KL plus LM. And again, that's called the segment addition postulate. We can always break up a segment in this way. Obviously, the letters may be different depending on the names of the different points, but the idea is the same. The big segment can be broken up into smaller pieces that are all added together. That is what our segment addition postulate allows. So we're doing this in a proof structure right now. We wrote the generic equation just using the letters, and we stated the reason for that. So I'm actually going to put some lines here and kind of make this using our 2-column proof structure. So we have our kind of our work over here on the left and our reasonings over here on the right. From there, we can make a substitution. We have expressions that represent all of these different segment lengths, and that's using the substitution property of equality. We know that Km is this, 5x minus 4. We know KL is x plus 3, and we know LM is 2x minus 1. So we now have an equation for ourselves. At this point, what we're going to be doing is now solving. But this extra step up here, these first 2 steps, are how we can incorporate some geometry into the proofs that we were doing yesterday that just involved solving equations. So this is how we're injecting just a little bit of geometry into the process. This right here is our geometry part. All right, what do we do now? In this problem, we'd probably put together like terms on the right side. So x plus 2x, 3x, 3 plus -1 is 2. You could call this substitution because you replaced x and 2x with 3x, and you replaced 3 and -1 with 2. But I usually like to call this simplifying, because all we're doing is kind of putting together like terms that are on the same side. I'm okay with either of these 2 reasons. It doesn't matter to me which one you use. The textbook might use substitution property. That's why that's typed out there for you. But when we're doing it, I'm okay if you just say it's simplifying. All right. And then, what did we do here? So what happened here? Let's take a look at these 2 equations and see what changed. Okay, the 3x is gone, and this 5x turned into 2x. So looks like what they did was they subtracted 3x minus 3x. So what do we call that when we subtract from both sides? The subtraction property of equality, right? So we subtracted from both sides. All right, just kind of looking at the equation, right? We need to get this number over to the other side. So we're going to be adding 4 to both sides. That seems to be the most obvious thing that we'd be doing here. It would be to add 4. So that's going to be the addition property of equality. Adding 4 would get rid of that, and it'll become 6. And then the final step when we're solving this is we're going to be dividing by 2, right? So dividing by 2, that's our division property of equality. And we got our final answer. Yep, you were totally right. X equals 3. A couple people sent me that already. This is a proof. This is solving a geometry problem in a proof structure where we have justified each step using some property or some postulate or something that really very succinctly gives us a reason that we were able to do the step that we did. So we're sneaking in some geometry concepts in there into this idea of algebraic proof. Same thing, and it might seem like we're doing a little too much here, but we got to understand what's going on and how this structure works so that we can apply it to geometry problems. All right. Okay, so there are a few geometry concepts that we're going to kind of be putting in there. So the first one are these two concepts of the segment addition postulate, which we just used in the previous problem. We can also throw in angle addition postulate. That's the same thing, but with angles. A couple other things that are important around those same ideas is the definition of a midpoint. You might not know that, but what the definition of a midpoint is basically if you have a midpoint, then the two parts are equal. So if this is our midpoint of this segment, the definition would say that AM is equal to BM. These two segments here and here are equal to each other. That's what the definition of a midpoint is. And the definition of an angle bisector, remember an angle bisector is when you have a line that cuts an angle in half. It's saying that these two angles here and here are equal. So the measure of angle 1 is equal to the measure of angle 2. Since these help us set up an equation, we might use these two concepts here to set up equations. So this one here, the segment addition postulate, angle addition postulate, they're used to help us set up an equation that involves either angles or segments. And these are used because when we know we have a midpoint, we know we have two equal parts, or when we know we have an angle bisector, we know we have two equal angles. So those could also be used to help us set up equations. That's kind of why we're going to be having these involved in our algebraic proofs, because these two different sets of properties and definitions are helping us set up equations. All right, let's take a look here. Here's an example again. We have if this is our given information here. This is where we're starting at. So we know that B is the midpoint of AC. That's some additional information there. Then AC is, so we're going to try to prove that AC, the whole length here, is equal to 20. Okay. So this is going to be a proof. So we're going to set this up using our regular kind of 2-column proof. And let me get my drawing back. So since we know that B is the midpoint, we know that AB, that segment right here, has to be equal to BC. That is the definition of a midpoint. So there we go. We use one of those properties from that last page to set up an equation. Now we're going to substitute. Instead of AB, we can use this, 5x. And instead of BC, we can use this, 3x plus 4. That is using the substitution property of equality. Now it's a matter of solving. So now this is a solving problem. We're gonna subtract 3x from both sides. So that is the subtraction property of equality. That leaves us with 2x equals 4. And then our final step for solving purposes, but not our final step for the whole problem, is this. We divide by 2. That is the division property. So we get x equals 2. Now, again, got to do a little bit of extra work here because our goal, remember, is to show that AC is equal to 20. So we need to do a little bit more here. We need to figure out an expression or something that could represent AC. So what I'm going to do is write an equation using the segment addition postulate. So I'm going to say that AC is equal to AB plus BC. That is the segment addition postulate. And I can now sort of plug in these numbers here. I can kind of actually evaluate what AC is going to be equal to. This is totally running out of space, so I think I can lift it up. Okay. Move that one too. I was running out of space there, so. All right, so that means that AC is going to equal 5x plus 3x plus 4. And if we plug that all in, we end up with 5 times 2 plus 3 times 2 plus 4. Both of these two steps are using the substitution property. Right? I substituted in these expressions. Yeah, substituted in these expressions here for that. And then I also substituted in a number for x because we just solved for x right there. And then just with a little bit of simplifying. So if we just kind of evaluate this whole thing, we end up with 10 plus 6 plus 4. We get 20 after some simplifying. This is not one that I would expect you to be able to do kind of on your own at this point, just because, not that you couldn't solve this problem. I think that most of you could solve this problem. The proof structure and kind of showing all of the formal steps is where it might get a little bit confusing in there. Because notice I didn't really leave anything out. I showed all my work. I justified every step with one of these properties of equality and so on. So it's just important to note that it's a lot. There's a lot of different things that we're doing here and a lot of different properties to keep in our mind. What I'm going to be having you guys do and what most of the focus is going to be on in the homework for this section is all about these solving steps and these properties of equality. Eventually, through the next section, we'll kind of get into those different things. Yeah, so the point being is we were trying to prove this conditional statement. We started with this piece right here, and we were trying to end up with this conclusion, essentially. So, and most of the time we can write the concept of our proof as a conditional statement like this. And all of these steps are how we got from this hypothesis to this conclusion. All right, I'm going to go ahead and clear this off and kind of do the last couple things here. So in geometry, there are a few properties of congruence that we need to know. I'm just going to write them all down. These are all related to the properties of equality. Congruent is a slightly different thing. Remember that this is right here. This is our congruent symbol. Congruent is what we use for geometric shapes. We say that this shape is congruent to this other shape. It basically means two things. It means it's the same shape and it's the same size. So congruent is a little more detailed, a little stronger than just saying equal. Because equal just means that the numbers are the same. And we don't use equal when we're talking about shapes. We use equal when we're talking about maybe the parts of the shape, like the length of a segment, or the measurement of an angle, or like the area of a triangle. When we're talking about specific measurements, we can use equal. But when we're talking about the whole shape, we have to use this idea of congruence. So there's 3 properties of congruence that we need to know, and they're basically the same thing as properties of equality. Something is always congruent to itself. So if you have a segment EF, it is the same shape and the same size as itself, obviously. Something, there's called the symmetric property of congruence. So if you have 2 angles, if angle 1 is congruent to angle 2, you can flip that. It doesn't matter the order. You can say angle 2 is congruent to angle 1. Seems silly, but it's true, right? It doesn't matter. If they're the same size and shape, it doesn't matter which side of the congruent sign where it's on. And the last one is transitive. That's actually going to be pretty important. That's going to come up a fair amount when we start talking about triangles, but we can kind of create a chain of congruence the same way we could create a chain of equal. So we can say this segment is equal to this segment, which is equal to this segment. And so we can kind of shortcut that and say that the first one is congruent to the second one, to the last one. And that's nice to be able to do that with the transitive property. That's something we will do a lot later on in geometric proofs. We'll use a transitive property a lot. All right, and then 11 o'clock, we have 4 minutes. Let me clear what I have. Again, we're not going to use a lot of these right now in just 2.5, but it is important to know. All right, so let's look at these. What property justifies this statement? So we're looking for either property of equality or property of congruence. Which property do we think this is? Well, as I'm looking at it, the symbol is giving me at least a hint of the beginning. I'm using the equal sign, so this is some property of equality. And since I have the same thing on both sides, this is what's called the reflexive property. Reflexive property is when you say something is equal to itself or something is congruent to itself. And this is the property of equality rather than the property of congruent. So reflexive property of equality. Here we go. We have angle ABC is congruent to angle ABC. So reflexive property again, because something is congruent to itself, but this time reflexive property of congruence. Small distinction, but when we're doing proofs, it's actually somewhat important. Here we go. Segment XY is congruent to segment VW. Segment VW is congruent to segment XY. That's where we switched the sides. It's symmetrical. So we call that the symmetric property of congruence because, again, we're using congruent in there. Here we go. Angle 1 is congruent to angle 2. Angle 2 is congruent to angle 3. So angle 1 is congruent to angle 3. This is that transitive property. We created this chain of congruence. We said that angle 1 is congruent to angle 2, which is congruent to angle 3. And so instead, we shortcutted that and said 1 was congruent to 3. That's the transitive property. Zero is equal to A is equal to X, so 0 is equal to X. Again, we're creating a chain. 0 equals A A equals X, so 0 equals X. This is another example of the transitive property, but small difference, transitive property of equality. We're talking about equals here. So just knowing which one of those properties we're talking about is going to be important here. All right. Homework, there's a fair number of problems. Pay attention to which ones you need to turn in. Number 19 and number 23, those are going to be the two that you need to turn in for credit. This is going to be actually the only assignment for this week, so don't worry about anything else. Just make sure you get this homework in and anything that you may be missing from other weeks. With the shortened week, I decided to change things up a little bit. I have office hours today at 1:30. Please make sure you come, and if you need help. So grades were due yesterday at 7:30 for your quarter 1 grade.